When the James Webb Space Telescope, JWST, released its first deep space observations, astronomers expected sharper images, better measurements, and perhaps a few exciting surprises. What they did not expect was to find galaxies that seemed to exist far too early in the history of the universe. These discoveries have sparked one of the most fascinating scientific debates in modern astronomy. Some headlines claimed that the James Webb Telescope had broken the universe, while others suggested that everything scientists believed about cosmic evolution might need to be rewritten. Although those headlines are dramatic, they reflect a genuine scientific mystery. The universe has always surprised us, and James Webb is revealing details that were completely invisible before. Instead of proving that previous theories were wrong, Webb is challenging researchers to improve their understanding of how the earliest galaxies formed and evolved. To understand why these observations are so important, we first need to travel back nearly 13.8 billion years to the beginning of the universe. According to the Big Bang model, the universe started as an incredibly hot and dense state before expanding and cooling over billions of years. After several 100,000 years, atoms formed, allowing light to travel freely through space. Then came what astronomers call the cosmic dark ages, a period before the first stars began to shine. Eventually, gravity pulled clouds of hydrogen and helium together, creating the first stars. These stars gathered into the earliest galaxies, which gradually merged and grew into the enormous spiral and elliptical galaxies we see today. For decades, this timeline matched observations from telescopes such as the Hubble Space Telescope, giving scientists confidence that they understood the broad picture of cosmic evolution. The Hubble Space Telescope transformed astronomy by allowing researchers to look billions of years into the past. Its famous deep-field images revealed thousands of distant galaxies packed into tiny regions of the sky. Because light takes time to travel, observing distant galaxies means looking back in time. A galaxy located 13 billion light-years away appears as it existed 13 billion years ago. Hubble found many young galaxies, but they generally appeared small, irregular, and relatively undeveloped, fitting predictions that galaxies should gradually become larger and more complex over billions of years. Scientists expected that the James Webb Space Telescope, with its much larger mirror and infrared capabilities, would extend Hubble's discoveries by finding even younger and fainter galaxies. James Webb, however, exceeded every expectation almost immediately. Equipped with a massive 6.5-meter gold-coated mirror and highly sensitive infrared instruments, Webb can observe wavelengths of light stretched by the expansion of the universe. This allows it to detect objects whose visible light has shifted into the infrared after traveling across billions of light-years. Within months of beginning scientific operations, Webb identified hundreds of galaxy candidates dating to less than 500 million years after the Big Bang. Some appeared surprisingly bright, surprisingly massive, and unexpectedly well-organized. Instead of finding only tiny collections of newly formed stars, astronomers saw galaxies that looked remarkably mature for such an early period in cosmic history. These observations sparked excitement because they seemed to challenge the predicted pace of galaxy formation. According to standard cosmological models, the first galaxies should have taken time to accumulate stars through repeated mergers and steady gas accretion. Yet Webb appeared to reveal galaxies containing billions of stars when the universe was only a few 100 million years old. Some researchers initially estimated that these galaxies possessed masses similar to the Milky Way despite existing when the universe was less than 4% of its current age. If those estimates were correct, galaxies somehow assembled much faster than computer simulations had predicted. The scientific community quickly began investigating whether these observations truly represented impossible galaxies or whether something else explained the surprising data. One possibility involved uncertainties in measuring distances. Determining the distance to extremely remote galaxies is difficult because astronomers often rely on photometric estimates using brightness at different wavelengths. These methods are powerful but not perfect. Later spectroscopic observations, which provide more precise measurements, showed that some early galaxy candidates were indeed as distant as first believed, while others turned out to be closer than initially estimated. This refinement reduced some of the apparent tension but did not eliminate the mystery entirely. Another explanation focused on stellar populations. The earliest stars likely differed significantly from stars forming today. They may have been hotter, brighter, and much more massive. If early galaxies contained large numbers of these luminous stars, they could appear much more massive than they actually were. Brightness does not always equal mass. Astronomers realized that assumptions developed using nearby galaxies might not accurately describe galaxies that formed shortly after the Big Bang. By updating models of early stellar evolution, scientists found that some Webb galaxies could fit existing cosmological theories more comfortably. Even so, several galaxies remained unusually impressive. Some displayed organized structures, active star formation, and central regions that hinted at rapid growth. Webb also discovered surprisingly early supermassive black holes. These enormous black holes, containing millions of solar masses, appeared when the universe was still remarkably young. Their existence raises another fascinating question. How did black holes grow so rapidly? Did they begin from unusually massive seeds? Did they experience extraordinary feeding episodes? Or do entirely new mechanisms operate in the early universe? These questions remain open, making Webb's discoveries even more exciting. One reason scientists are cautious about claiming that the universe is broken is because astronomy has experienced similar moments before. Throughout history, new telescopes have repeatedly uncovered observations that challenged existing models. Sometimes theories required significant adjustments. Other times, better data resolved the apparent contradictions. Scientific progress depends on testing ideas against new evidence rather than assuming existing knowledge is perfect. James Webb represents the most powerful observational tool ever built for infrared astronomy, meaning it naturally reveals objects previous telescopes simply could not detect. Discovering unexpected phenomena is exactly what scientists hoped would happen. The phrase "impossible galaxies" has become popular online because it captures public imagination. In reality, these galaxies are not impossible in the literal sense. Instead, they are unexpected under previous assumptions. As researchers collect additional observations, many of these galaxies are proving compatible with revised models of star formation, gas dynamics, and dark matter behavior. Rather than overturning cosmology, Webb is helping scientists refine it. The standard model of cosmology, known as lambda-CDM, continues to explain a remarkable range of observations, including the cosmic microwave background, the expansion of the universe, and the large-scale distribution of galaxies. Webb's discoveries are testing the details of galaxy formation rather than disproving the overall framework. Another remarkable aspect of Webb's observations is the extraordinary diversity among early galaxies. Some are compact and dense, while others appear surprisingly extended. Some are actively forming stars at incredible rates, while others already show signs of more stable structures. This diversity suggests that galaxy evolution may have proceeded along multiple pathways much earlier than scientists previously imagined. Instead of following one universal timeline, galaxies may have experienced different growth histories depending on local environments, available gas, nearby companions, and the influence of dark matter halos. Dark matter itself remains one of astronomy's greatest mysteries. Although invisible, dark matter appears to provide most of the gravitational framework upon which galaxies form. Webb cannot observe dark matter directly, but its discoveries may help scientists better understand how dark matter influenced the earliest stages of cosmic evolution. If galaxies assembled faster than expected, perhaps dark matter clumped together differently under certain conditions, accelerating the collapse of ordinary matter into stars. Alternatively, improved simulations incorporating more realistic physics may reproduce Webb's observations without requiring any fundamental changes to cosmology. Webb is also transforming our understanding of chemical evolution. The first generations of stars created heavier elements such as carbon, oxygen, silicon, and iron through nuclear fusion. When these stars reached the ends of their lives, they enriched surrounding gas, enabling future generations of stars and planets to form from increasingly complex material. Surprisingly, Webb has detected evidence of chemically enriched galaxies relatively early in cosmic history. This implies that star formation and stellar evolution progressed rapidly, producing multiple generations of stars in less time than previously believed. Equally exciting are Webb's observations of gravitational lensing. Massive galaxy clusters bend space-time, magnifying even more distant galaxies behind them. Using these natural cosmic lenses, Webb can detect objects that would otherwise remain invisible. These observations extend humanity's vision closer to the dawn of cosmic history than ever before. Every new deep-field image contains thousands of galaxies, each representing a chapter in the universe's evolutionary story. Some may challenge existing theories, while others reinforce them, but together they provide an unprecedented record of cosmic history. The impact of these discoveries extends far beyond professional astronomy. They remind us that science is a constantly evolving process rather than a collection of permanent answers. Every generation builds upon previous knowledge while remaining open to revision when better evidence becomes available. James Webb demonstrates the remarkable power of curiosity-driven exploration. Engineers, scientists, and international space agencies spent decades designing a telescope capable of answering questions that had not even been imagined when construction began. Now those investments are producing discoveries that inspire new questions instead of simply confirming old ones. Media headlines often portray scientific discoveries as dramatic revolutions, but reality is usually more nuanced. The universe rarely abandons its fundamental rules overnight. Instead, our understanding gradually becomes more precise as observations improve. Webb's discoveries fit this pattern beautifully. Rather than breaking physics, the telescope is exposing the limitations of earlier assumptions and encouraging researchers to develop more sophisticated models. This process represents science functioning exactly as intended. Observations challenge theories, theories evolve, and new predictions are tested through further observations. Future observations will provide even clearer answers. Webb continues surveying larger portions of the sky while observing galaxies across different stages of cosmic history. Ground-based observatories, including extremely large telescopes currently under construction, will complement Webb's findings with detailed spectroscopy and higher-resolution measurements. Together, these instruments will allow astronomers to estimate galaxy masses more accurately, measure star formation rates, analyze chemical compositions, and trace the growth of black holes throughout cosmic history. As data accumulate, many current mysteries will likely become clearer, while entirely new puzzles may emerge. Ultimately, the greatest achievement of the James Webb Space Telescope is not that it has broken the universe, but that it has expanded humanity's ability to explore it. Every unexpected galaxy, every unusually massive black hole, and every ancient cluster of stars reminds us that the cosmos is more complex and fascinating than anyone imagined. Webb is revealing that the early universe was not a simple, quiet place, but a dynamic environment where stars ignited, galaxies assembled, and black holes grew with astonishing speed. Whether these discoveries require modest refinements or significant theoretical advances, they represent exactly what scientific exploration is meant to accomplish. In the years ahead, astronomers will continue debating the meaning of Webb's remarkable observations. Some apparent contradictions may disappear as measurements become more precise. Others may lead to entirely new ideas about the formation of galaxies, the behavior of dark matter, or the earliest moments after the Big Bang. Whatever the outcome, James Webb has already secured its place as one of humanity's greatest scientific achievements. It has shown us galaxies that formed when the universe was still in its infancy, opened windows into cosmic epochs never before observed, and reminded the world that the greatest discoveries often begin with a simple realization: the universe still has countless secrets waiting to be uncovered.